Hi everyone, and welcome to today's live webinar on designing for sheet metal fabrication. First, I'd like to introduce, I'm Serena, and I'm on the marketing team here at Xometry. A couple of quick notes before we get started. Please submit your questions throughout the webinar in the question box. I'll be monitoring the questions as they come in, so feel free to submit them at any time, and our panelists, Greg and Callye, will answer these questions at the end. Stick around till the end of the webinar for a special discount code just for our attendees. And finally, after the webinar, we'll send you a recording so you can share with your colleagues or watch this webinar again. Next, I want to introduce our first presenter and your host, Greg Paulsen. Greg is here he is, the Director of Application Engineering here at Xometry. He brings over 10 years of experience and leadership to our team and is an expert on all things additive manufacturing, machining, and injection molding. He's also the star of our Engineering Challenge and X-Tile video series. You may have seen them on our YouTube video channel, or sorry, our Xometry YouTube channel. So head on over after that for more fun content. Greg is joined by Callye Keen of K-Form and Red Blue Collective. He is currently the design manager at K-Form, a machining and sheet metal manufacturing company. Callye practically grew up in the manufacturing industry, transitioning from production to design to management. Through K-Form, he works with defense industry organizations to manufacture and assemble rugged electronics enclosures. He's also the co-founder of Red Blue Collective, a product development consultancy. Through Red Blue Collective, Callye offers his expertise and network to entrepreneurs looking to launch and grow physical product companies. He is active in the startup and maker communities as an advocate for manufacturing. So thanks again for tuning in, and don't forget to submit your questions in the webinar question box. With that, I'll pass it over to Greg.
All right, thanks so much. And again, thank you, Serena, for putting on this webinar, making sure we got the right people on board, including Callye, who I've known professionally for probably about 5+ years now. Whether through interactions with Xometry as a customer, but also Callye as a consultant on product development, and Callye as a machine shop / product development company owner and designer. So I've consulted with him a lot, and especially on the sheet metal webinar, he's been invaluable because he's there making parts, designing parts, and kind of fixing some designs along the way too. So he knows the back and forth between sheet metal. So today is talking about design for sheet metal. I'm going to get started for those who are new and those who just joined on the webinar, talking about Xometry just very quickly. We're going to go through some helpful resources through our website, as well as show a quick quote demo about how you can actually quote sheet metal parts instantly on Xometry's platform. We're then going to talk about the process itself. Sheet metal is like engineered origami, and knowing the tools of the trade will help you be mindful of your design along the way. And then we're going to go into specific design guidelines for sheet metal. At the end of this webinar, we are going to take all the questions that you ask and try to answer as many as possible. We love the Q&A, so please continue to add questions along the way, and we'll get to them at the end of the webinar. So let me get started just talking about Xometry and what we do here. Xometry is there to solve this problem of procuring custom manufactured parts. We have an instant pricing system where you as a designer can actually upload that 3D file, or even use a CAD add-in in SolidWorks or Inventor, get instant pricing and lead times through a multitude of processes. We have 7 3D printing processes. We do sheet metal, CNC machining, urethane casting, and injection molding as well. Beyond that, so we can go anywhere from prototype to production through this online quoting platform, and you just click buy. On the manufacturing end, we have manufacturing partners, and these partners each have their own specific talents and capabilities. Some of them are machine shops that do high-spec aerospace manufacturing. Some of those are shops that love that low-volume work. And of course, we have also the 3D printing bureaus, which usually have an incorporation of several technologies at one time. But across this network, we're able to pair your project with those who are best able to produce that. And these are Xometry qualified and we hold to the standards and expectations that we promise within our quote. So it's really exciting for us because we don't have a capacity issue. We are able to distribute this through our manufacturing network of professionals. So if you don't have a part ready yet, I always want to bring Xometry as also a resource for you. So I'm going to actually move to the live site real quick and show you a little bit about our site and some of my favorite spots on this, as well as do a live quoting demo for you. So I always like to go to the resources tab as far as a get to know your process goes. Our design guides are a fantastic place to stop. So you may be the best sheet metal designer on the planet, or maybe you're at this webinar to learn a little bit more about it, but you can actually dive deeper into every process that we offer through our specific design guides. If you don't know what to choose, I also recommend our production guide, which is kind of a 2-pager per process we offer. Our design guides, we actually update them as we learn more, including I actually learned some more doing this webinar, so I'm going to be updating our fabrication design guide soon here. And we also add as we add processes. So actually, our newest one is Carbon DLS. I'm just giving a shout out there because we did a webinar last week on that, and the Carbon DLS Ultimate Guide is up and live on our site. I also recommend on our resources page, you could go check out our FAQs. It's exactly what it stands for. The most common questions that come inbound to us, we have answers for you right away. We also have other more detailed explanations of things like surface finishes, manufacturing standards, etc. From these pages. So please check out our resources, and if you're ready to start your project, you go ahead and just click Get a Quote. So our online quoting system accepts most file types that you're already designing in, whether it's a solid part, an IPT, a step file. You can take that and upload it to your quote. I actually added a little sheet bend part here, so whenever you upload a part, you could actually, it'll actually save it in your parts library so you can access it later. And I'm going to show you how quick it is to get a sheet metal quote. Click Add Files. And this part just instantly priced. So when the Xometry engine interprets a part, it'll actually price out in the least expensive material. In this case, this is 3D printed SLS nylon 12, which is a great commodity material for prototyping, but obviously it's nylon, so it'll be a little more flexible than a sheet metal part. So let's go ahead and make this a sheet metal project. I'm going to click Modify Part. You'll get a 3D view with some basic information about your part here. I'm going to click Process, move down to the Process Sheet Metal, and then you can see our material selections for sheet metal right here. I'm going to go ahead and actually move this to probably the most common sheet stock that we use, which is 5052 aluminum. And you can see the price instantly updates. So at quantity 1, I have a $263 sticker on this for this part. This part's about 9.8 inches by 5.2 inches, kind of giving you a size there. And you can further customize by adding things like finishes to your parts. If you have a part that has threads, tap holes, or inserts, you can specify there. So let's say this part has 2 inserts. The price will instantly update. Specify tighter tolerances. Even if you have something that's a box that requires weldments, you can specify that. It will instantly update. Part marking. So oftentimes we see parts that require silk screen. That's just a click away. And even inspection reports. One thing to note here is that we actually do recommend for sheet metal projects to upload a drawing. Although it's not necessary, especially if you're doing spec or spec production work, the drawing is extremely useful, and we'll go into that during this webinar here. And if you do have anything like even a DXF flat pattern, it does help for reference as well. So your price and lead time instantly updates. I have this 5052 part, 2 inserts in the locations, and even by changing quantities, you'll see how quickly sheet metal amortizes in pricing. Because a lot of that is getting that initial setup and tooling in place, and then as you keep on making more and more, the economy of scale just keeps on getting better and better. And we'll go more into that, but this is one of the biggest reasons why sheet metal products are so proliferated all around you right now. It's kind of one of those that scales almost like an injection mold part, where it just has that you make your setups and you just repeat. So let's talk about the process a little bit. So I'm going to move back to my presentation here. Just real quick, again, mention that we do sheet metal, obviously. We do plastic 3D printing. We 3D printed metals. We do CNC machining, urethane casting, and injection molding. So all that is encompassed on that website. I just showed you the sheet metal portion, but it's just as easy to quote for any of these other processes. But Callye, I want to bring it to you. Let's talk some sheet metal fabrication.
All right. So everyone, thank you for joining us again. Thank you, Greg. So I love sheet metal. I've made a million sheet metal parts, literally. Literally. And there's a lot of advantages to it. I mean, we think of I think machining gets a lot of love in the industry right now, and we see a lot of cool machined parts. But there's some serious when we're talking about volume, we can get extremely affordable, high-quality parts out of it. It scales to volume production, even with straightforward, and we'll be talking about probably the most common best practice approaches to sheet metal, not the super high-end, fancy type volume production, but you'll see prices reduce greatly just by using the normal processes that you'd see in the in shops across the nation. So I think we think of aluminum right now, and we think of it kind of as a cheaper material. It was really the first super material, right? And it has an amazing high strength to weight ratio, and that's one of the reasons that we have such fantastic aircraft, right? And you can leverage that kind of power in your designs to make fun sheet metal parts. So it's also effective for very large parts, just like planes. So you can make the outside skin of a Boeing aircraft, or you can make a small little bracket.
Yeah, and I know we just did a case study for essentially a garage for a reusable drone, and the part that Xometry made post-fold was, I think, a little over 4 feet. So it's like kind of this entire sheet enclosure, which for the ruggedization and for the practical use of it, you would not machine it, you wouldn't 3D print it like sheet.
Next slide.
Yep.
There we go. Okay, so sheet metal, the name, it's made from common flat stock. So a place like K-Form will get pallets and pallets stacked high of 4x10 or 5x12 or whatever dimensional stock that we buy from our vendor, literally tens of thousands of pounds a week. So sheet from of that part. So you'll hear that called profiling or blanking, and we'll go over a couple of those processes. And then the part is formed using tooling. So that's how we get that box shape or that bracket shape. We subsequently can use ancillary processes to put inserts. So we'll talk a little bit about PEM nuts, rivets. We can weld. We can apply a huge variety of surface finishes, just like machine parts. And then we can do different types of part markings to get a finished good. Should be updated.
Okay. There we go.
It's coming.
It's coming, guys. I'm good. Yeah. So I have material stock sizes, but the thing's not updating. Give me a moment here. I'm going to refresh my screen. All right. I'm going to check a view really quick. My screen's not updating on this. Give us a second, guys.
So when Greg was using the quoting portal, we saw that big list of different materials, and aluminum, steel, stainless, copper, brass. So that's another nice thing about sheet metal, is that we have a wide variety of materials to choose from. Each of those materials have their own alloys and blends and options, but you can see the chart there. That's the gauge chart. Some of the materials, this is America, also come in fractional sizes, so 32nd, 16th, 8th inch, that as well. And if you're overseas, particularly aluminum and steels can come in fractional and sizes. So if you're in Europe, that would be 0.5 millimeter, millimeter, that kind of thing. Cutting platforms, we see that 4x10 is pretty standard for what somebody's laser or water jet would be. Seeing more and more moving towards the bigger sheet, just because handling is the labor and that's where the cost is. The machines are so fast that the bigger the sheet, the better. So we're seeing lots of like 5x12 and even like 6 foot by X feet, like 20 feet. But good rule of thumb, if you want the widest variety of shops to be able to quote your part, 4x10 is good. No part bigger than what can fit in that rectangle. Right.
And just want to double check here. I should be on a screen that has flat pattern preparation. Okay.
Yep.
So it's updated. All right.
Yep.
Just want to double check. We were having a screen delay happening on our side.
So when we talk about flat pattern, I'm sure lots of you use SolidWorks or Inventor or another one of those packages, Fusion, that allows you to create sheet metal and then unfold it flat. So it's created a flat pattern, and then we can use a variety of different processes to create that pattern. And depending on which one you choose, it can do some or all of those features. So there's trade-offs in everything. That's why there's different machines, or shops like Kform, why we have really just one of each of these machines, because they all have their efficiencies and good and bad qualities, or I wouldn't say bad qualities, I'd say they're gives and takes, right? So water jet, pretty good accuracy, fairly slow, but it can cut anything. So people always ask when they see the water jet, how thick can it cut? I say anything that you can squeeze underneath that head, that's what it's going to cut. But reasonably, it can cut very thick gauges in comparison to the other processes. Laser cutting, probably the most common process that you're seeing right now, is because it's extremely high accuracy. The cost of fiber lasers has really come down and the speed has gone up. So those are extremely highly accurate hole-to-hole, feature-to-feature, very fast. So we can cut 16th inch steel at 1,000 inches a minute, just for reference, right? So
it's wild to watch.
It's pretty fast.
Yeah.
Like the head moves so quickly, it would scare you the first time you see it. You can cut thinner gauges of materials. So down below, I know Greg in the last slide said, like, man, we want to avoid foil cutting, but you can cut very thin things. We can cut up to 1 inch thick steel, and we can cut up to 3/4 aluminum on our particular machine, just for reference. But you can only cut metal. It's best for metals. CO2 lasers can cut some wood, but we're not really concerned with that today. Best for metals. Plasma is kind of like, I think of it as a blend, kind of in between. It's good accuracy, so kind of maybe in some ways not as good as water jet. It puts a lot of heat into the part, so you could worry about distortion possibly. It's higher speed, and you can do thick gauges and metal only, obviously. Yeah.
Now just talk about edges real quick. So I know water jet tends to have a slight taper on the edge curve, and that's because you're shooting essentially abrasive water flow through, and it has like almost a slight curve out pattern. Laser, because of the gauges, you don't see that as much, or what like you see it looks a little bit cleaner.
Yeah. Particularly in the fiber lasers now, because a CO2 laser, imagine cutting with a 0.01 end mil, right? And it distorts when it hits the material, and it can do certain materials better than others. CO2 laser can't cut reflective materials, kind of slows down on some stainless some blends of stainless, right? Fiber laser is between 1/3 and 1/10 the size. The beam is literally 1/10 of the size, but it has twice as much energy, right? So it's very, very condensed, and what you get because of that is you get incredibly crisp edges. So what we're seeing right now with our 4 kilowatt laser is we're seeing a lot of small gauges with no finishing afterwards. So, yeah. All right. Okay. So then subsequently the blank will be moved. It would be moved to a process to form it. We mentioned shears here just for material preparation, particularly some of the machines you might want to cut a smaller, cut a smaller blank and put it on the machine. So you'll see that in sheet metal, notchers, other pieces of material equipment. But brakes, like you see there, that punch and die, that press brake, and that's used for angular bending, multiple bends. Yeah.
All right. And so this is a slide that we're talking about. So we have our forming tools, right? We're making our parts here using different types of things, usually a brake, some punch press, different types of forming tools. But how do you feel when you just get a flat pattern?
So when I just get the flat pattern, I always have to ask for the 3D model. I always have to ask for a complete drawing because we're responsible for the part to work, right, and to be dimensionally accurate. And in general, unless you work in or run a fabrication facility, your flat pattern is going to be wrong, right? That's the long and short of it. I wish that SolidWorks or Inventor was smart and said, hey, I know exactly how to unfold this and it's going to be accurate. But if you want ±5 or ±10 bend to bend, you're probably not going to get it with your automatic unfold.
Yeah. So we have our CAD drawings so with the 3D model giving you that purpose, usually a drawing saying, for example, I always talk about the drawer, like, are you the drawer or are you the cabinet? So what's important for you is the inner dimensions of that design, or is it the outer dimensions? Is this part fitting into something else?
Yeah.
Is just really important. And actually, I should have put a note on here, but one of the most common things I see on the DFM side is seeing both the inner and outer dimension on a drawing for like the inside wall and the outside wall, and ultimately best practice for sheet metal is choose one. Just because you're dealing with a gauge of metal anyway, so one of those dimensions is moved, and by having both, you're actually not indicating what's the most important thing to you on that project. Also, just a quick question on K factor. Can you give me a good explanation of K factor?
Yeah. So there's a couple of calculations that you can make to properly unfold sheet metal, and you can input those into the sheet metal properties in your CAD software. One of those more common calculations is K factor, and you can go on a number of websites and get a lookup table and then plug that back in to your CAD software and get more accurate unfolds. But K factor is essentially the neutral line in between the compression and expansion of the material as it forms up. It's going to be different based on bottom forming, coining, or air bending. You're seeing air bending in that picture where the form doesn't hit the V incomplete. But yeah, go look up the table. You'll get more accurate parts. You'll probably get better parts back from your vendor. If you're doing 90-degree bends, that top die that you saw in the other picture is 88 degrees. So most likely, that's to account for spring back. So you're most likely doing bottom bending. So if you look at the table, pick the bottom bending number.
That's good to know. I didn't. I just learned that. Awesome. So this is all moving into designing. So Callye, I'm going to bring you in along the way here. But when we're designing for sheet metal, there's going to be some best practices and rules to go by.
Sure.
And again, this all has to do with the actual process. I'm working with a flat sheet. I'm using tools that have certain advantages and disadvantages to them. So angular bends, for example, even cutting that blank out, creating that profile, all those tools are a little bit different. They all work together very well, but being mindful of those is going to give you the best results. And starting with that, just talking about general tolerances of sheet metal, the tolerances get a little layered here because I have a tolerance, for example, if I'm doing a laser or any flat profile cut, it's going to be very similar to CNC where a lot of these location tolerances are going to be right around plus or minus 5 thousandths. But then once you go into things like edge to feature and then you start adding bends, a bend itself all of a sudden will bring in about 10 thou added to that. Because you have little movements and motions that happen within that metal when you're bending. So when you look at Xometry's website and you look at our general tolerance for sheet metal, you'll see 20 thou. But just understand that 20 thou is because the assumption there is in a bend condition. Because you're adding at least 1 or 2 bends, you're adding that extra tolerance, extra wiggle into your design. If you have 2 holes on those features, again, they have more of a machine-like tolerance because I'm using something with a linear XY that's creating that feature. So this is on our website, but I do want to point out that general tolerances tend to have these layers to them, whether it's a forming or bending tolerance, bend to hole, linear dimensions, diameters, all those things come into mind, even angularity, which is like that angle of bend there. So let's talk about bending. Best practices. I am looking for a 1-to-1 material thickness to bend. So if I have a 1/4 inch plate, I'm going to have a 1/4 inch internal radii on my part. If you want to go to a minimum, I really don't recommend designing for minimums, but if you need to, about 1/32 under material thickness is the minimum. Again, my recommendation always is I don't drive my brakes in their lowest condition or my tires in their lowest condition. The same thing happens when you're designing and engineering is by going to minimums, you're going to be inherently adding risk without specialized tooling. Also think about these operations. I'm taking a part up to a brake. I'm putting this into the brake, running the operation. If I have the same bend, so if I have a bend that is going almost like a C shape or one direction flat, and then I curl back in in the same direction, I can often do this in the same operations as an operator. That saves setup time and will save you money, especially in production runs where you're doing multiple pieces. Also, keeping this radii consistent in your design means that I'm using the same tool to create each one of those radii. So as you add different radii, you'll be also adding a different die setup for those parts there. And the other more common thing overall, just talking about material stock, and we talk about bends in general for this, is if you're used to machining and you're building stuff in 6061, 6061 is an incredible material. It is it's lightweight, has a high strength ratio to it. It's just very purposeful. But understand that if I take a flat piece of aluminum 6061 and try to crease that forward, it is inherently more brittle than many materials that are used for sheet metal. So when you're moving from process to process, understanding that you may actually need to move the type of material. Aluminum 5052 is much more forgiving as a sheet metal material, where I may not want to mill that as often as I would do 6061, but I definitely want to use it for sheet metal if we're moving to those. So just understand that your most common sheet metal aluminum is 5052, where if you're CNC machining, it's going to be 6061. A little note that I have here is if you do have any lugs and flanges, consider calling out grain direction. So typically you want to bend perpendicular to the grain so if you imagine a grain like as a long strings of crystallization of the metal, if you bend with it, you'll be more prone to seeing some cracks in those grains. But if you bend against it, so perpendicular, you'll have a much stronger bend with less risk of cracking. So here's my quick animation here, but the other thing though is when you're bending, note that I need to have a design that needs to bridge that entire V-block section, because if not, when I put a press down, these strong hydraulic driven presses, it could actually pull the operator and pull your part forward and not actually create those features. So when we talk about minimum flange length, to resolve those minimum flange lengths, but basically the goal there is leverage on the other side, plus a little bit more, and there's some equations that can help figure that out, especially if you're actually a press operator with that. And your flange width itself should be about 4x material thickness to that. But this is all about me being able to get this feature into a tool, secure in a location where it can have leverage on both sides to create that proper former shape. On this graphic, I did also want to just kind of show a back gauge here, because typically in manufacturing sheet metal parts, I'm going to be taking a flat piece. I have this gauge already calibrated to the right location. I bump up my part against that gauge, press down, create that feature. So that's just something I wanted to point out as well. So it's all about the bends with sheet metal. It's all about bending, forming, creating the best out of your designs. If you imagine taking a sheet of paper, cutting a hole in that sheet of paper, and bending right in the middle of the hole, you'll probably see that the edges of those holes are going to flare outwards. If you start rotating that paper where that hole is and getting right at where the bend's right at the edge of that hole, you'll see it creates like a little lower lip. Exact same thing happens in metal. So you want to think about feature to feature depending on the feature, and look at these best practices. So these best practices are based on material thickness. So we have for example, if I'm designing a countersink feature, so I have a hole with a countersink feature in it, I want to make sure that my countersink holes are at least 8x material thickness distance away, so that the geometry of one part doesn't affect the other part. Same thing with countersink to any feature, essentially. So countersink to edges, to slots, to the outer bend of the radii of your bent part. You want to keep that further away. Hole is the same example, about 6x material thickness away from the edge of your bend is best practice. I look at this as edge of hole, not hole center. Same thing with edge of slot. So
just make a larger hole.
Yeah, just make a larger hole. Yeah. So, but that's something that's extremely common. And I know we're about to talk about relief cuts and other things. There's some ways to mitigate this, but it's an extremely common thing that we see is features too close to the edge. It's not always holes. It's sometimes, say for example, I'm making a router box and I have a port for like a VGA cable or something going through. Very common for me to see those ports and see it being designed right next to a bend, and it creates almost like this. It looks like a fat lip. It'll curl out on that, and because that stress is going somewhere, it's going right into your feature set. So we have this best practice is also available on our design guide. But it's just something to kind of keep in mind and be mindful of. We can do countersinks in this process. So it's the only thing that I'm recommending right now for basic sheet metal where you can actually carve into the sheet a little bit versus doing a form like a bending feature. This is typically done by hand. There's some tools that can do this as well. Just you don't want a countersink to go fully through that sheet product. You want it to actually go no more than about 60% of your material thickness through. You need a little bit of that hole to show still. Counterboards, don't do them. You just stop making a sheet metal project. When you add counterboards, that's me milling a feature into these, and you just made a CNC part. So think flat, guys. Countersinks are okay because I can usually use a hand tool for that. Counterboards, all of a sudden I'm milling, and we're gonna have a bad day. Some basics around designs and finesses. At least half the material thickness for fillets in general, both internal and external fillets. And then very, very important, if you want to maintain features of your design, like kind of like almost have a crisp, clean looking part afterwards, relief cuts. Every time I bend, I'm putting stress into my part of material. If I create relief cuts, it allows that stress to just go in that feature set and not expand out to the more of your part. So a relief cut, like this piece here, allows me to do this bend without this outer edge, which could be an indexing feature, for example, or a nice like side for a weld, will not be affected, where all the stress actually goes right into the bend feature. Extremely useful to add to any project that you're working on. There's also, although this drawing, and realistically, the relief cuts notches I usually will make round here, but having cuts along the bend also prevent that edge from kind of flaring out when you're bending the material. So sometimes if you imagine curling up a box, you'll see some flaring out right on the edge. Simply design in some snips there. That flare will still exist to a degree, but at least it won't be interfering with the outer dimensions of the project. I'm also going to note that, just running back to my best practices for holes slide, sometimes if your hole is a little closer to the edge, I could do like a 0.5 millimeter laser cut, or basically a little relief cut right below it, almost like an underscore, right, parallel to the edge there. And what it does is that little underscore is going to flare out, but your hole won't. So sometimes you can do that to mitigate for parts that are not right near edge. And I think, Callye, we were talking about even sometimes you could just outline the hole with almost a 3-sided box, creating a relief cut right near a bend, and the hole just turns into a diving board next to your bend.
Yep. That's extra helpful if you need to put the PEM hardware, which we're going to talk in a second, in, because there you have a lot of center to hole to edge constraints on that hardware. So.
And yeah, installing hardware, if your hole all of a sudden becomes an oval or has a big flare out lip, again, you're going to have a bad day. So yeah, talking about PEM hardware. This is not an advertisement for PEM fasteners, but they just kind of own the market with sheet metal parts. You can tap sheet metal. I'll say that, and I'll admit to that. But typically, I like adding hardware inserts into the design. So these are installed in a way like a rivet, where they're almost like squaged and blended with the material once they're installed. So they're permanent installations onto your sheet metal project. And you can add features. You can add a dimension, like something that you would have to traditionally machine, like bosses, pin, like studs, standoffs, even mounting features. There's so much available. PEMengineering.com is a great resource for you to look at PEM fasteners in particular. But the variety is huge, and they're used literally everywhere in the sheet metal project. The one thing I see on drawing discrepancy sometimes is when you're uploading your file to Xometry, you're usually uploading the file almost like in the nude there. It doesn't have the PEM inserts installed. We're not uploading assembly. So make sure that in your drawing, it's explicit in which direction we're installing that. Oftentimes we could kind of intuit where it is, but we never want to make an assumption and send that to you. So if you design in, just understand that not just install PEM here, but install PEM on this side, because we don't want your project to have interference. We want to make the project successful for your project.
That's a really good note. I mean, people in production, they're not going to have access to your 3D model at the hardware insertion machine. So having the drawing at least specify the direction is super, super helpful.
Absolutely. And again, I can't stress this enough. It's a way to make, you can look at this part picture here. It's a way to add so much functionality to your part, PCB mounts, even like I said, I think this part actually, you kind of see on the side has some cable guidance, even parallel holes, so a way to make a feature hole so you can put a lid on the parts without actually doing a fold in. It's pretty cool, clever stuff. So the last thing, of course, we can install inserts. We could also do welding. It's very common on discrete manufactured parts to have welding a seam, either if it's tacking something together or even full weld seams. We can do all of this at Xometry. This example here shows that, first off, a relief cut. Woohoo! I got my relief cut here. I have my fold in this location. And then I'm actually welding on the inside of the part to create a nice join here. By doing that, you don't have any of this external seams that you'll see typically with welding. Welding has an advantage where It is mechanically stronger. It can be specified for things like a seal, so if you do need sealing surfaces, you can do a full weld there. It's something you need to particularly call out, though, through our notes and through your drawing. Just understand it's high heat. Obviously, depending on the gauge you use, it may distort your part or its features. It also requires a welder. That's a specialized job, and believe me, they're worth every penny, and sometimes you got to pay for it depending on the weldments that are needed. So there are alternatives to welding as well, especially as you're scaling up and you find out that labor cost becomes some of the most expensive part of your project, and that's where I'm going to lean into rivets. Callye, can you give me some examples of like where you've decided to go from weld to rivet on your projects?
Yeah, so this tab or complex tabs like this where we fold in, if I want to make a bracket and I want it to be really strong and I bend in another tab, I can actually bend it all together and then I can put a pop rivet in. And the nice part about rivets is I don't necessarily have to have access to the inside of something. So if I bend something up and I wouldn't have that access, the pop rivet is where I would go. And there's a variety of those from aluminum all the way up to extremely rugged rivets that we use in aerospace. And they all have different properties. But one of my favorite things about it is just one of the portions of my job as a quality assurance manager is that it's very repeatable. I don't need the same level of skill as I would need in a certified welder. And I can scale that process up. It's very easy to get one person to do it or 10 people to do it. It's fast. Yeah. I can also automate it fairly easily. So
yeah, and I will also say it saves you on complex setups. So if we are doing a very large component and bending that out, sometimes you have to set up your welding setup. You need to do that edge where the riveting tools are often much more transportable.
Yeah.
It's often handheld.
Large parts is we've made a lot of electronics enclosure sheds, like really small buildings that you can transport around. And you could weld it together if you wanted to, but riveting is definitely a perfect application for that. Yeah, absolutely.
So let's talk about everything we talked about so far is common tooling. Stuff that most sheet metal shops have available. Even things like welding, rivets, adding inserts, angular bends. Very commoditized, and also very job shop-esque, which means if you upload that part, we can make a part, and you're just paying for that part, and relative setup to it. When I talk about formed and stamped features, I have some examples here where whenever you see kind of a third dimension pop out of your flat part, even if you look at these little features, so you have a little joggle feature, but those holes are popping out a little bit. And of course, this one, you have this organic curvature along the edge. That's not a straight break. That is a formed or stamped feature. And to make formed or stamped features, you need a die set. So these die sets are just like tooling, think injection molding. You are getting charged upfront for that tooling. It takes time to make that tooling, so you just added lead time to your project. And if you have low volumes, oftentimes my challenge with you is how can I turn this into angular bends for my low volume project or shift to a different material, because oftentimes the price and lead time may not add value to your project for low volume. But stamping, stamp features, form features tend to have much higher value when it comes to production. So think like 1,000+ units. That's where all of a sudden I can add multiple features in one operation or two operations very quickly together and complete parts. So these pieces right here may have been completed in one step, both the bending, hole formation, and cutting, all done with a die set. So you can do some really, really unique stuff with metal forming. Just understand that it is much more for that design for production aspect, maybe part consolidation aspect that sheet metal can do, but it is more of an engineering project than it is for a direct to make project.
Designers and engineers need jobs too.
Yeah, yeah.
You know, this is where really communicating with somebody that knows those processes can save you literally hundreds of thousands or millions of dollars, right? But yeah.
And I just put in some stuff that's more readily available because it's one of those, almost like in CNC machining, for example, we often do not charge you for taps or even the gauges that we use to check those taps because we probably already done that work before, so we already have the tools, or we're expected to have those tools in place. I can usually find louvers, so think like those vents on lockers. That feature tends to be more readily available. Gussets, which is almost a kind of a way of adding a rib without adding a rib, where you're actually forming like, imagine my thumb impression in the middle of a 90 degree bend. Joggles, which is kind of like this feature right here. It's actually really useful where you're just kind of offsetting the plane a little bit. Like I think it's like 1 material thickness by 1 material thickness. And actually, I'm looking around me right now. We have some like wall mounts that are joggles, and so you have one of these joggles here mounted to the wall, one of those joggles mounted to your picture or frame that you're hanging up, and they slide right into each other, still flush to the wall. So they're really useful features. Curls, think a piano hinge, so like something that's actually curling up around. And hems, which is a stiffening feature to your part. So hems are a fold back. Sometimes it's an open fold back, sometimes it's more like a pinch close fold back, but those tend to be more readily available from a tooled or formed feature versus things like these images here where you have this multiple contour. That's the only part in the world with that contour. So just understand that some stuff tends to be more commoditized, but a lot of these, if you have a specialized need, it's going to be, you almost want to consider like an injection mold project where it's not just click and go. It's usually a couple consults figuring out what's the best for your needs. And as Callye mentioned, could save you a boatload if you're able to simplify those features. So I talk all about these features, and I say, hey man, isn't angular features, aren't they better anyways? Like because again, if you're doing low volume production, angular features are just readily available. We get bend parts right away. So sheet metal surface finishing options are almost identical to what you do with CNC machining. Metals are metals. So very often I see chem film parts. We do see some plated parts. A lot of powder coat in sheet metal, so that's just one click away. Anodization, even color anodize is very common, and of course all those part markings. So silk laser stamping, we could do all that. Also, if you choose custom finish on our website, upload a drawing, we can look at masked operations like chem film, mask with powder coat, anodizing, masking with, or anodizing plus part marking, et cetera, et cetera. So we can expand on beyond just one finish and go with us. I mean, it's something extremely common for us to do. All right, guys, so get your questions ready. I know Serena has some tools in her tool belt here. I just want to mention really quick that we do have live engineering support on Xometry site. So if anywhere between 8 to 9 p.m. Eastern, you can actually get a hold of us live, whether it's by phone or by chat or by email. We're there to help you out, as well as check out our FAQs, check out those guides that I mentioned beforehand. All the stuff is here to help you and help you grow as an engineer and designer. We want you to learn and use these processes right because there's so much value in these, especially sheet metal. I mean, it almost seems like an underdog sometimes, but those who use it realize how incredibly valuable it is for a production line. And Serena, I'll bring it to you here.
Sure. So guys, we have a discount code here for you all to use since you stayed till the end. You can use Fabricate to get $50 off your next order of $100 or more. We will also send this discount code in the email along with the recording after this webinar for all of our attendees, as well as webinar registrants. Xometry will also be at Fabtech on November 11th to 14th in Chicago. Look out for our booth A4343 to say hi and talk more about Xometry and sheet metal fabrication.
Yeah, if you guys haven't been to the Fabtech show, it's kind of wonderful, especially if you're in the world of like bending and forming parts. And I like to go on the shop floor itself and just see all the new demonstrations. I get mesmerized. There are some stuff like punch presses that are actually forming entire parts while they're still on the press, and like the technology just keeps on advancing. It's very exciting.
Amazing robotics.
Yeah, you actually just picked up some really nice equipment for your shop that I've been geeking out at. It has almost like a SolidWorks instance in the actual machine, so it's doing unfolding, checking, and saying like, you didn't do that right. Adjust it here. All right, now do it. Put these tools in.
Everything's super high tech now. I mean, that's like another whole webinar conversation. But I mean, manufacturing is amazing right now.
We'll pin this in a few months from now. The next gen manufacturing.
Next gen manufacturing.
I like it. All right, so yeah, let's talk. I know we have some questions on board, so let's get. I know, right? Yeah, ask us anything.
All right, well, we have a couple of questions. First and foremost, about drawings.
Mm-hmm.
Do you need to include the PEM hole tolerance on the drawing?
I'll give you my statement, and Callye, call me out if I'm incorrect here, but just like any other inserts, I'm usually designing my features to what's recommended on that site for that particular insert. So you should have a part ID in mind when you're doing that. So there's going to be a minimum hole diameter. I do recommend the min diameter. Just like tapped holes, we run into this often where something's modeled in the maximum condition, then all of a sudden you throw your fastener in and it's just like wobbling around loose. Yeah, so we could always make a hole bigger, but it's very hard to make one smaller. It usually means toss it, redo it. But you should see guidance per item that you're using.
Yeah, I mean, so drawings are like our communication to everyone in the production facility, and us in the office or us in manufacturing engineering, like we have access to all the tools, but not everyone else necessarily will. So it's just a couple clicks away to put the proper tolerance in there, or if that's difficult, to actually just show the PEM hardware in there to communicate like this is the side that it goes in, and that hole is for a fastener, and your shop will know, hey, that this is it. And I mean, but communication, you're communicating with somebody through the internet or hundreds of miles or thousands of miles away, it could save you a lot of money just to add a couple clicks.
Yeah, and just a note on Xometry side, if you do have a solid part file and you have inserts installed and it's still in it's a multi-body file, I do recommend, like, our site will essentially block assemblies because we want you to upload discrete parts, because that's kind of how we think we make discrete parts. If you suppress them, save it out, upload it, that should be sufficient, and that also allows us to essentially unsuppress it, find things like orientation. So it's always helpful to have as many tools as possible to make sure that we get the influence right on what you're trying to work on. A drawing and a picture is worth 1,000 words, though. Yeah.
All right, great. And a related question here.
Mm-hmm.
Should someone call out a PEM installation as from near side and from far side? What's your recommendation on that?
Callye, I'll leave that to you.
Yeah. So the modern PEM inserters can feed from the bottom die or the top. Old school ones only feed from the top, or their manual insertion from the top or bottom. So I don't think that it would really be a preference one way or the other, just for clarity. What I personally do, because I'm really paranoid, and is I actually make a drawing of the assembly, and I'll show the stud its direction, I'll show the PEM's direction, and I'll call it out with a bubble and have a bomb. That's what we do internally, just because I've had one, literally getting one part wrong one time pays for me to make that drawing probably for the rest of my life. So, but yeah, we used to just say from near side or from far side in the notes, and I haven't seen any advantage of just always showing it one way, because you'll paint yourself in an engineering corner, drafting corner that way. Yeah.
I'm also going to chime in with what our head of quality, Jason McClure, says all the time, which is it's okay to go to another page on your drawing. we are able to press right or left on the PDFs that we have open. And if you have something that's just nice, clear, for example, what Callye mentioned, an assembly view with a BOM, it's just extremely useful, especially if we know we're doing multiple component order, which you can do on Xometry, and we can actually have some sort of thought check beyond just dimensional. We can actually have a reality check what you're intending to do with your project.
So we're going paperless next year, so it's even more of that. It's just paperless. PDF can be as long as I want. So
yeah, exactly.
Okay, so we have a couple of questions also on welding. First one here, does Xometry offer spot welding for fabrications?
Yes. So we can offer just about any type of weldment that you're looking for like common standard weldments. I will say it's just important to, this is where drawing comes in, because on our website, when you're selecting weldments, you're just selecting like how many, because that's enough for us to appropriately price those parts out. But those details really have to be included with the drawing, including specific callouts on what type of weld you want. If not, what will happen is about within 24 hours of your order, you'll probably get a call from one of our DFM engineers asking that question, saying like, all right, so you say weld, what do you really want here? And making sure that we're quoting it appropriately and that we're getting that project out appropriately.
Great. And I do see some very specific questions here.
Mm-hmm.
After the webinar, please feel free to reach out to Greg or Callye with your specific questions,
mm-hmm.
And then they can talk through that.
And yeah, as we're answering these too, if you do have any questions that are specific to a project you're working on, feel free to ask them here. I'll make sure I look at all our questions after these webinars, and I make sure that we have we get some specific guidance. So I want to get back to 100% of you.
Okay, so we're nearing the end of time. We'll do like 2 more questions
mm-hmm.
here.
Yeah.
All right. So here's another one. Can form flow drilling be done along with the extended tap?
All right. So Callye, I'll let you answer some of this because we talk about form in place projects, and I'll let you go into some of those options. Yeah.
So more and more shops have that capability. There's actually a huge variety of in-sheet forming that's available now, and it's pretty crazy what you can do, like inner flanges, flange lances, like tab and slot and joggle and sheet stuff. But each of those times that you do it, just bear in mind that, because this is why I love product design in general, is like you set up these boundaries of rules and say this is like what everyone can do, this is what some people can do, and then you get to a point where it's like this is what most people could do custom, but like as you pick those different things, you're just less and less vendors. So that's where Xometry's DFM team or your local fabricators DFM would come in and say like, hey, do you have this capability? Hey, I love working with you guys, but can you do this actual tool? Because you can do anything, right? Yeah. It's just like, what's the cost, or how many shops are on the 2,000 shops that are on Xometry? How many of them have a hydraulic turret press punch that has like that specific hole forming and tapping tool, like an Amada EMK or something like that.
Yeah, and again, it's something that we're happy to review, but typically our process would start if you know that, as Callye said, it's something that's probably more niche than general manufacturing. This goes for any type of form, feature, or hole. We do want to do a manual review, preferably pre-sale, because we're able to get some of our pre-sale and application engineers on board taking a look at the project. Because DFM is usually there to kind of the spot check, validate, and then if they see something come up, kind of work between the designer and our manufacturing partners, make sure they have a good blend. We do it on the pre-sale side, so as part of the quoting effort, it usually becomes this end-to-end success chain without any unexpected interruptions along the way.
All right. Last question here. What are the large radius stock tooling options? For example, an inch or a quarter inch.
So this is a kind of a question of like, when do I go from a radii to a form feature? Is that kind of how I'm reading it, or?
Yeah. So what's nice about large forms is that in general, and this is geometry depending, like you can multi-stage bend them, right? So let's say that I have a part and all of the forms in it are 16th inner radius, but then I have a 1-inch bend. We'd call it bump bending. You bend it multiple times, and our CAM software actually computes how many times it's going to have to hit that part to get that smooth radius. And that's custom tooling aside. There's a lot of really fun tools that are out there right now, but again, not everybody is going to have like a multi-stage a punch where I can adjust the inner radius on the fly, or like the different rubber dies and like roller dies and all those things, because they're really expensive. Like, but yeah, you can do progressive bends, and you can get that larger radii that you want.
Okay, thank you so much, Callye and Greg, for answering those questions and for sharing your wealth of knowledge on sheet metal fabrication. Callye, thank you so much for being our special guest today.
Hey, thank you.
And you guys, we will be sending out a webinar recording. We had a couple of questions on that. So look out for that, as well as the coupon code that you can use by the end of August. Last words, Greg?
No, I'm just very excited, Callye. I can't thank you enough. I mean, it's been excellent having you on board. And sheet metal for me, I know enough to be dangerous, but it's actually one of the few manufacturing processes that I haven't been on, on the press and figuring out. And so I've learned so much just working on this webinar and building it up, and your knowledge has been invaluable. So thanks so much.
Thanks, Greg.
All right.
All right.
Thank you, guys. Bye-bye.
Guys, take care.